We need to marinate more in chapter 4. Did I say marinate? About math. Revel in chapter 4, continuous distributions. Explore them a little bit more, both by hand and with technology. Imagine possible uses and do some things that are pretty cool, I think, today. So more with continuous distributions, continuous random variables is another way to say that. We've talked about normal distributions and some other complicated things like the gamma distribution already, but let's do something simpler to start with today. Let's do a continuous uniform distribution. Now, I did talk maybe 3-4 weeks ago about discrete uniform distributions where you have a finite set of possibilities, like with rolling a die, and there were 6 possibilities total that all had equally likely outcome, and X, the random variable, was the outcome 1 through 6. Each outcome had probability 1/6, and we saw that the graph of the PMF consisted of a bunch of, well, dots that each had a probability of 1/6 effectively. And we computed the mean and the variance and that kind of thing. We can do the same kind of thing with a continuous uniform distribution. But how does that differ from a discrete? Well, it's going to be a continuous random variable, X, uniform on some interval, meaning over some interval of numbers, real numbers, a continuum. What would it mean to be uniform? How about a PDF whose graph is horizontal? Constant. Now, it can't be constant, some positive constant everywhere, because then it would integrate to infinity, and it wouldn't be a PDF anymore. So it's got to be a finite length interval that we're talking about. The simplest would be the interval from 0 to 1. But we can do an arbitrary interval, say from A to B, where A is assumed to be less than B. What would the PDF look like? Here's a number line, A here, B here. We want it to be some positive constant value between A and B and 0 otherwise, right? It's got to be 0 otherwise. What is that positive constant value? Call it C. It's got to be chosen so the area under the graph is 1, so that it integrates to 1, right? To be a valid probability density function, it's got to integrate to 1. Well, it's a rectangle. You can figure this out without calculus. Area of a rectangle is base times height. The base is B minus A. The height is C. C would have to be 1 over B minus A in order for the total area to equal 1. You don't even have to write any integrals. In terms of a formula, you want to be technical about it. You want to write it as a piecewise formula. Little f of x is the constant 1 over B minus A if x is between A and B, and 0 otherwise. But wait a minute, should I use strict less than signs or less than or equal to's? What do you guess the answer is? It doesn't matter. Okay. Again, with continuous random variables, the probability of equaling a specific real number exactly to infinite precision is 0. In effect, when you observe a value of a continuous random variable, like a length, you measure a length or an amount of time or something like that, or an area or a volume, you are, there's measurement error, right? You come up with a number, but does it really have a length exactly equal to 4.7 meters? Probably not. Really, because of measurement error, what you're really measuring is a little tiny interval of possibilities. You're not saying the length is exactly 4.7 meters, because it would be impossible to measure with that precision. That's another reason why, from a modeling perspective, it makes sense to say the probability that a continuous random variable takes on some real value exactly is 0. Graphically, the area under a curve above one number or below one number, meaning the area of a line is 0 because lines don't have any area. Anyway, it doesn't matter whether I use strict less thans or less than or equal to's. Again, OW means otherwise. And there's what the graph looks like. What would the graph of the CDF look like? The CDF is still always, whether your variable is discrete, continuous, or mixed, the probability that capital X is less than or equal to little x. Capital X is the abstract random variable. Little x can take on any real value. This is a function of little x. In the case where the variable is continuous, it is the integral from minus infinity to little x of the PDF, and it is traditional, and I think a good idea to use some other variable here besides x, like t or u or whatever you want to use. Actually, I like using Greek letters a lot. Sometimes I use it. My favorite Greek letter is called xi, and it looks really, really beautiful. It looks like that. It's beautiful if you make it slowly. It's also kind of fun to make fast, but it's hard to do it so it looks beautiful. Squiggle is what you might also want to call it. Oh, the official Greek name is xi, but I didn't use that there, so I'm crossing that out now. Crossing out squiggles with, how could I have crossed that out? It's so beautiful. Okay. I was just doing that for fun. That's what it is in general. In this particular example, what does that mean? Well, if x is less than a, you're integrating to 0. Once you get to a, then this function starts increasing because you start accumulating areas. If x is right here, say, then the area that's accumulated right there would be base times height. X minus a over b minus a is going to be the area of what I shaded there, right? Base is x minus a. Height is 1 over b minus a. Multiply those. It's the same as x minus a divided by b minus a. And ultimately, what you're going to get here is a linear function that grows from 0 up to 1 as x grows from a to b. This value right there is 1. X minus a over b minus a is the area that I shaded up here. It's also, for the given value of x, the second coordinate of this point right there. That's x minus a over b minus a. It's a linear function over this interval with a slope of 1 over b minus a. And its value when x is a is 0. Plug in x equals a. There you get 0. And its value when x equals b is 1. B minus a over b minus a is 1. So if I was going to write down a piecewise formula for capital F of x, it's going to be 0 if x is less than a, say less than or equal to a, but I could say less than a. It's going to be x minus a over b minus a if x is between a and b, and it's going to be 1 if x is greater than or equal to b. If you want to find probabilities for this uniform random variable, like what's the probability? Let's take a particular a and b. Let's say a is 0 and b is 2. What's the probability that x is between 1 and 1.5? That is the same as integrating 1 over 2 minus 0 from 1 to 1.5. By the fundamental theorem of the calculus, that's also the same as f of 1.5, capital F of 1.5 minus capital F of 1. What is capital F going to be here on that interval? It's going to be a is 0, b is 2. X minus 0 over 2, x over 2 is what capital F is going to be when x is between 0 and 2. So this is going to be 1.5 over 2 minus 1 over 2. 3/4 minus 1/2. If I've not made a mistake, that'll be 1/4, 0.25. Look good to people? A is 0, B is 2 is what I'm doing here. What else would be interested in a uniform distribution? The same things we're always interested in. What's the mean? What's the variance? What's the standard deviation? Maybe what's the moment generating function? Well, the moment generating function would help us find the mean and the variance. But we could also use the definition of the mean and variance. Maybe we should do it both ways. Maybe with technology help to save some time. We could find third and fourth and fifth and sixth moments too. Are those of any use? Actually, they are, at least the third and fourth. What are they useful for? For describing the shape of the distribution. I'm not going to go into details today, but maybe on Thursday. Let's go ahead and find the mean, the first moment, by the definition of the expected value. And we'll also find the moment generating function from the answer, but we should be able to predict the answer actually, right? This distribution is symmetric. The mean is supposed to be a center of mass. The mean better be halfway between A and B. It better be A plus B over 2. That better be the answer if this is going to make any sense. You can predict the answer in this case ahead of time, not always. Try it with the definition. So we need to integrate in general from minus infinity to infinity, x times the PDF. So in this case, if the PDF is 1 over b minus a, I'm doing the general case here, arbitrary a and b. I'm going to integrate from a to b, x over b minus a. That's really integrating a linear function. I'm going to get a quadratic, x squared. Don't forget to divide by 2 as well. X goes from a to b. I'm going to get, in the end, b squared minus a squared over 2 times b minus a. Doesn't look like b plus a over 2, does it? Or is there something I can do to help me see that the answer actually is a plus b over 2? Factor the top, yeah, b minus a times b plus a. Oh, the b minus a's cancel, how nice. B plus a over 2. We've confirmed what we guess the answer should be. I could do the second moment by an integral. I could integrate effectively x squared over b minus a, get x cubed over b minus a, 3 times b minus a. That's probably worth doing because it's worth practicing because we're going to have to factor the difference of 2 cubes. Let's do that. Expected value of x squared ultimately will be the integral from a to b of x squared over b minus a. That'll give us x cubed over 3 times b minus a, x going from a to b. That'll be b cubed minus a cubed over 3 times b minus a. All math majors should know. You know, I know you're not all math majors, but some of your engineering majors, some computer science. Okay, even engineers and computer science majors should know you can always factor the difference of 2 cubes. Really? Yeah, in this case, b cubed minus a cubed is b minus a times what? It's not the product of 2 binomials. It's a binomial times a trinomial with 3 terms. And what are those 3 terms? They are b squared plus ab plus a squared. You want to check it, you'd have to multiply it out. What happens is a bunch of stuff cancels. And yes, this is an AB here, it's not a 2AB. Oh, the b minus a's cancel. Let me put the a first, since a comes before b in the alphabet. A squared plus ab plus b squared over 3. Is that the variance? No, don't think that's the variance, right? Don't make that mistake. It's the second moment. So the variance, second moment minus the square of the first moment. Do I really want to do this? A squared plus AB plus B squared over 3 minus A plus B over 2 quantity squared. And ultimately, if you think about it, we're going to have to get a common denominator of 12. Yes, I do want to do this because the variance turns out fairly nice in the end. So I'm about to simplify this on the next page here. Variance of X, okay. Get a common denominator of, yeah, I want a common denominator of 12. So I need to, with this first fraction, multiply the top and the bottom by 4. 4a squared plus 4ab plus 4b squared. Minus, when I square this one, I'll also have to multiply the top and the bottom by 3. Because 2 squared is 4, and I have to multiply 4 by 3 to get 12. Use parentheses here to be careful. So I'll multiply the top and the bottom after squaring by 3. So I'll get 3a squared plus 6ab plus 3b squared all over 12. And yes, a bunch of stuff cancels. 4a squared minus 3a squared is a squared. 4ab minus 6ab is minus 2ab. And 4b squared minus 3b squared is plus b squared. And that can be factored. And did I make a mistake? As a minus b. No, this is correct. A minus b quantity squared over 12. Which, since b is bigger than a, you might prefer writing as b minus a squared over 12. They're the same thing. It's not too complicated. And it does imply the standard deviation of x as the square root of the variance of x is really, well, in general, it would be the absolute value of b minus a over the square root of 12. But since b is bigger than a, this is the same as b minus a over the square root of 12. Since a is less than b, b is bigger than a. Square root of 12, of course, that's also square root of 3 times square root of 4, which is 2 square root of 3. You could also write it like this. It doesn't really matter much. You can also just leave it as square root of 12. You could rationalize the denominator. I don't care. Okay, that is what the standard deviation ends up being. What's 1 over square root of 12, just to get an approximation for this? 1 divided by square root of 12 is about 0.2887. This is about 0.2887 times b minus a. Coming back to our 2 standard deviation rule of thumb, almost all the probabilities within 2 standard deviations of the mean. 2 times sigma x is going to be about, well, multiply this by 2, 0.5774 times b minus a. So if you think about this graphically, here's a, here's b, here's the mean. The mean is a plus b over 2. These distances here and here are both b minus a over 2. In other words, 1/2 times b minus a, 0.5 times b minus a, and 2 standard deviations is a bit bigger than that. So yes, all the probabilities within 2 standard deviations of the mean in this case. With the normal curve, that's not all the probability. It's about 95% of the probability. But with the uniform distribution, 100%, all the probability is within 2 standard deviations of the mean. Moment generating function, is that worth finding out? Let's go ahead and do so. Let's just do it with Mathematica. You'd have to integrate e to the tx over b minus a. Is that hard to do by hand? From a to b, well, this is the calculation you'd have to do to calculate the moment generating function. Because remember, the moment generating function is the expected value of e to the tx. This e in Mathematica, by the way, is the number e, not the expected value operator. Is that hard to do by hand? Well, it's not too bad. you're integrating with respect to x, you would treat the t as a constant when you do the integral. You get a factor of 1 over t when you do so. And you'll have an e to the tb and an e to the ta. Yeah, there's a factor of t in the bottom there. So this is evidently the moment generating function for such a uniform random variable. Let me copy and paste this. The fancy looking e is also the number e. Is m prime of 0 equal to b, a plus b over 2 indeterminate? It's because, okay, yeah, it's because technically speaking, the moment generating function is undefined at t equals 0 here. It's actually a removable discontinuity. And if you remove the discontinuity, it actually even becomes a differentiable function. There's a hole in the graph. I'm not going to go into details. If we were actually to compute m prime of t with Mathematica in this case, I think we'd want to do this. M prime of 0 could be computed as this limit, and that is a plus b over 2. It's not computing m prime of 0 directly because you're dividing by 0. I mean, even m of 0 is undetermined, right? You're dividing by 0. But it's really a removable discontinuity. If you fill in the hole in the graph, it makes it a continuous function. It makes it also differentiable even. For the second moment, we could do it as a limit as well. And that's the same thing we got before. And we could take that answer and the square of the previous answer and simplify. And there's our variance. The percent sign refers to the preceding output. So for input 62, it's referring to output 61. The double percent sign refers to 2 previous outputs, output 60. So I'm taking this and subtracting the square of that and simplifying. What other fun things can we do here? How about using a random variate again? What did that do? That'll simulate sampling from a distribution, give you data, simulated data. How about, is uniform distribution built in? It is. Wait a minute, is that going to be continuous or discrete? I think it's probably continuous. Yeah, it says represents a continuous uniform distribution between min and max. The min is A, the max is B. Can you do discrete as well? Probably, but maybe as a different function. Discrete uniform distribution is how you do a discrete one. So let's pick A to be 0 and B to be 2 again. Well, I think I need these in a list like this. That's simulating from a uniform distribution on the interval from 0 to 2. If I want to simulate, say, 1,000 data points, there they are. There's 1,000 simulated data values between 0 and 2, according to a uniform distribution. Let's store that in a variable that I'll call data. And I'll use a semicolon so we don't actually see all the data. Semicolon suppress output. I could make one of those number line plots for data. The dots look pretty uniform, don't they? Okay, let's use 100 data points instead of 1,000. They're still somewhat uniform. Maybe it's easier to see with, say, 200 data points. Fairly uniform, reflecting the uniform distribution. You can also make a histogram, which is essentially a bar chart for the data, and see that the bars are fairly uniform in height, effectively keeping track of how many numbers are in each range here. Let's go back to maybe 1,000 data points. A little bit more uniform with the bar chart there. With 1,000 data points, we got close to 100 in each one of these intervals. Looks like the intervals are length 0.2, 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6. Looking at the horizontal axis here, 0.6 to 0.8. It's counting how many data values are in each one. You know, like we saw last week, you could compute the mean of the data, should be close to 1, right? A is 0, B is 2, averages that is 1. can compute the variance, should be close to b minus a squared over 12. 4 over 12, 1/3. Oops, variance of data. Close to 1/3. Standard deviation, close to the square root of that. Square root of that would be close to 0.6. We're computing with the mean variance and standard deviation here. We're computing the mean variance and standard deviation of data, not the distribution itself. Simulated data. We haven't talked about how to compute the mean, standard deviation, and variance of data. That comes in chapter 6. Not now, but we're having Mathematica computed, and maybe you've had a little stats in your past and computed those things. You do the simulation again, you get different answers. Different number line plot, different histogram, different mean, but still close to 1, different variance, but still close to 1/3, different standard deviation, but still close to 0.6.